You're Batman, and you need to keep your bat ears listening out for crime. You can't be everywhere at once. So how do you do it? You need to spin up your trusty bat computer and build yourself a crime-detecting audio classifier. So, how are we going to detect crime? Let's imagine you have hundreds of microphones dotted around the city. You need to build a machine learning model that will let you know when it hears a gunshot. We need to feed it audio data and classify that into crime. Here's a tool. When that light hits the sky, it's not just a call, it's a warning. But first, I need to build my machine learning app. Alfred, grab me a coffee.
So, for each microphone in the city, we're going to generate some audio clips. And then we'll load these into Python using the librosa package, and we'll load these in as waveforms. Now, waveforms aren't the easiest thing for machine learning models to interpret, so we actually need to transform this into something different. So what are we going to do? We're going to change our audio classification problem. That's a really bad ear. And we're going to turn it into an image classification problem, which is much easier for machine learning models to interpret. So, how are we going to do this? First, we need to convert our waveforms into something called a spectrogram. So let's take our waveform, and first we're going to perform something called an FFT, or a fast Fourier transform. And what this does is takes our waveform and produces frequency plot diagrams for a small sample in time for the waveform. And what this frequency diagram contains is a list of the frequencies on the x-axis and then their amplitude in the y. Think of amplitude like volume. So that's one FFT, so one slice of the waveform. So how do we actually produce the spectrogram? Now, a spectrogram is more akin to an image, which is what we want to get to. What this does is takes each of these FFTs and looks at them from the top and then plots that out like so. So imagine we've got high amplitude frequencies here, here, and here. So looking at it top down, we've got this kind of view here. And then we take another sample. And let's pretend it's exactly the same as this one for this here, here, and here. And then we keep doing that for different slices. Let's just imagine this gets a bit quieter as time goes on. Lower frequencies, higher frequencies dim out. So what we've got is time on the x-axis, our frequencies on the y, and then we've got a color coding system here, different ranges. Let's flesh out our spectrograph. So we have a color code here, and this is now the amplitude in, let's say, decibels. So now we've got something that looks more like an image, and we're going to feed this into our convolutional neural network with standard image classification approach techniques. So we're going to put together our convolutional neural network, feed in our spectrograms, which are converted audio waveforms, and out of this we will get our prediction of whether or not this is a gunshot, our crime detector. So let's get into coding our crime detector. We've got our Kaggle notebook open. So first we're going to import all of our dependencies, then we're going to import and have a look at our training data for the model. Then we're going to create the features, we're going to pull out that audio and create those spectrograms as we mentioned in the whiteboard session. Then we're going to actually build our model, which is a convolutional neural network, and then we're going to look at predicting out those audio classification sounds. Let's see if we can detect those gunshots. So let's get into it. I've pre-populated the libraries. We'll just go over them. So we have to install a additional library for the librosa audio package, resamp. That just lets us more efficiently load in some of those audio files and convert them. Then we've got the librosa library itself that we're going to use to load in those audio wave files and do some audio tweaking and pre-processing. Then we've got pandas for our data frames. We've got numpy for our arrays. We've imported random that we might use for sampling the audio clips. We've got matplotlib for plotting, and then we've got our model packages here. So sklearn model selection. We're not using the sklearn for modeling, but we're going to import the train test split because it's a useful function for train test splitting. Then from Keras, we've got a couple of functions, but the model itself is going to be sequential with some dense layers. And then we've got an IPython package here that just lets us play audio clips within the notebook itself. So let's load in the dataset. So you can see we've already added in the data from the Kaggle kind of data store. So we've got the Urban Sound 8K dataset, and what this is a mixture of different WAV files of various urban sounds. We'll have a look at the different classes later, but this could be our city scenario, as it were, where we've got all of our microphones set up. So it's laid out in different folds. I think the dataset owners put them in folds so you could do some different fold split testing, but today we're just going to use everything. So for that purpose, we're going to look at the meta file, the Urban Sound 8K meta file, to let us know how many clips, what the classes are, have a look at the labels, and then just see how we can read them in. If we run this function, then let's have a look at our metadata file. So let's take the head. So you can see we've got a list of all the different WAV file names, some IDs, start and end times indicating the length of the clips, salience, which we're not going to use today, the different folds that they're in, so the different folders, the class IDs, so numerical class identifier, which is helpful, we don't have to create that, and then the actual class name, so the sound itself. You can see we've got dog barking, children playing, so let's delve into those a little bit more and see if we can find out all the different classes within here. So this is easy as audio files. Then we'll reference the class and then call unique. So you can see we've got a number of different audio sounds in here: dog barking, children playing, a car horn, air conditioner, street music, the all-important gunshot, siren, engine idling, jackhammer, and drilling. So these are the different sounds in our cityscape that we're going to have to identify and then pass through to find our gunshot. So let's start loading in some of those audio files. So we'll take an initial audio file to load in, see if we can have a listen and see if it is what it says it is. So let's start referencing an index. So we want to pull in an audio file where the class is equal to gunshot. So let's see what the gunshots sound like first. And the class name is gunshot, and we're going to take the first within the array. So that's going to give us the index in that list. Audio files. So that's going to give us an index of the first kind of row that has a gunshot audio file in. So you can see it's 106. So we'll just rename that back to index. And then we want some way of passing through the audio file names. So we'll call this array, and we'll say mp array equal to the audio file's slice name. So we're referencing slice file name up here. So that's going to give us an array of different audio files. Then we want an array of the different fold names. So this is going to give us an accompanying array of all the different fold names attached to those slice file names. So we can start passing through the different folders up here. And then we want to return their class as well. So their accompanying class. And that should give us the information we can pass through. So what we're going to do is combine all these kind of different things together to give us the path for the audio file itself. So let's start loading in that audio file. We're going to use the Librosa package, so we can just call the Librosa.load, and we'll create that path, which let's put R so we can get in the forward slashes, and then we'll copy the file path here to get our start. So we're going to reference this Urban 8K file structure. We want to get into the fold for each of these audio files, and then we want to reference the slice name. So we need to add on a string of fold. So we're calling the fold array. We're going to reference the index that we've created. So we want to load in that gunshot file, and then we need to add another forward slash, and then we're going to call the string of the array, which is the slice file names, at the index. And then what this is going to give us is an audio and it's also going to give us a sample rate. So we can feed both of those things into our spectrogram. So the spectrogram knows how often the audio has been sampled in its frequency, so that we can match that up when the spectrogram is created. Let's call audio from the IPython package, and we're going to feed in our original audio data and the sample rate. And let's see if this loads. This should be rate equals. And we've got a bug. Oops, we've missed the word fold, so we just need to add fold onto here. And that should work. So we're referencing that fold structure here. Okay, so this should be a gunshot, so let's give it a little listen. That's most definitely a gunshot. That's what we're looking for. So let's have a look at that audio file visually. Let's visualize it. So first we'll visualize the waveform. So this is what we're talking about on the whiteboard. This is the original audio kind of structure. And this is what we want to convert from into a spectrogram. So let's load this up. So we've set up our code here. We're going to create a figure using matplotlib. We're going to load in and display our waveform with the Librosa display library. And then we've set some titles here just to make sure we know what we're looking at. We're good scientists. We label our axes. So this is the gunshot waveform, and the Y label is the amplitude of the waveform. And then the x-axis is, let's be good scientists, the x-axis is time. And we'll call that seconds. So you can see that kind of distinctive gunshot pattern that we heard. So let's just play that gunshot again. So you can see those two shots ringing out, so increasing in amplitude and then dropping off. So that's what the waveform looks like. But again, this isn't good for machine learning models to interpret. It's pretty difficult. So we want to convert this into a spectrogram. Now, as I mentioned before, a spectrogram is a kind of a top-down view of slices of this waveform converted to a frequency. So let's convert this waveform into a spectrogram piece by piece. So we'll have a look at the different frequency slices, samples using the FFT, and then we'll have a look at the spectrogram as a whole. So let's create our fast Fourier transform to have a look at how we convert this waveform into different frequency diagrams. We'll have a look at one of those frequency diagrams, and then we'll start piecing them together to create that spectrogram, as you remember from the whiteboard session. So we've got our code here. We're going to convert the amplitude to decibels just to give us a better scaling, because as you can see here, the amplitude is a pretty hard to interpret scale. And decibels tends to be easier for translating human voice and sound levels. Then we're going to use the Librosa STFT, which is short-term Fourier transform, or short-time Fourier transform, which is just a slightly different method of that fast Fourier transform. And then we're going to return the kind of max values out of that. So as you can see, we've got an array of shape 1025 by 113. So we can start interpreting some of these files. So let's have a look at the first one. So as you can see, this array is actually a kind of frequency diagram. So let's plot this out. So as you can see here, this is decibels versus frequency along the x-axis. This will become slightly more clear when we open up the spectrogram, but suffice to say, this gives us the audio transformed into those frequency peaks versus decibels. Now what we need to do, if you remember, we got this top-down view, and then mash all of these together for the whole array. So if we went across the whole array, 1000, you can see we've got these different kind of frequency peak diagrams. So let's have a look at the spectrogram as a whole. So we have our spectrogram here. So you can see that we've got our waveforms translated into those frequency diagrams, looking at those top down and then squashing those together. And this gives us a heat map image, importantly, of the different frequencies over the time and the amplitude scale for them. So you can see here those kind of low frequencies with the kind of white hot decibel levels. And then as you get up higher into the frequency range, you can see that the decibels value decreasing or increasing depending on how you want to look at the range. And then you can see that kind of dark patch at the top. So if we look back at the frequency range, you can see this kind of decreasing scale and a drop off. So that correlates to this. as a top-down one view, and then we just continue those frequency diagrams as we go along. So you can kind of see this drops off slightly more, which kind of represents this waterfall drop off here. So this is our spectrogram. This is our image that we want to feed into the model. So let's have a look at some other audio waveforms. We'll take a sample of some more from the repository just to give a good sense of what these look like. So let's write some code to do some random sampling and pull some of those out. We've generated some more spectrograms for some more audio clips. So as you can see, the difference in the types of audio spectrograms. We can see a jackhammer with this kind of constant different frequency range and decibels going through. A siren with this kind of funky looking spectral range. I'm sure some of that is the Doppler effect here that you can see in motion. Air conditioner again, some kind of consistent air conditioner noise. Jackhammer drilling. So we've got a few more. We could probably run this again just to get some more random audio file samples. So yeah, we can see some street music, engine idling, some children playing. So all these different kind of spectrogram forms that we can start to feed into our model. So we're going to do one last thing to our audio data before we start feeding this in. What we're going to do is convert our spectrograms to something called mel frequency spectrogram. Now this isn't completely necessary for this task. So what this does is convert the frequency range into something more akin to human hearing. So if you did have speech kind of classification models, this could be really useful. We'll run through this conversion anyway, just so you've got a good sense of what that looks like. So let's put the code together and we'll run through it. So we've got a code. What we're doing is very similar to what we've done previously. We're going to load in our audio data. So we're choosing our gunshot audio from before. We're going to then pull out the mel spectrogram specifically using the Librosa library from the feature subset of that library. So we're going to create our feature data set. We'll print out the shape of that feature and you can kind of see how that differs to the spectrogram we created before. Then we're going to load up the audio file and we're going to plot that out just so you guys can see what that looks like. So you can see this looks very similar to what we saw before with the spectrogram shape, but the frequency is kind of is reduced. The frequency range is reduced to more akin to human hearing. So you can see it's a bit more coarse and squashed together, and you can see that we've got a much smaller array, which makes processing a bit easier. So we've got a 128 by 113 array here, and this makes things a bit more efficient for processing speech classification audio, or in our situation, the kind of gunshot audio. So let's start creating our training data. We're going to pass all those features from the audio files into these mel spectrograms. We're going to put all that together in a big array data set that we can then feed into our convolutional neural network. So we need to start passing all of these different wave files into these spectrograms. This is going to take a little bit of time. We'll put the code together, walk through it, and then we'll set it running. Got our code. We're going to pull out all of the audio files in our data set. We're going to create our features and append them to the feature list, and then we're going to pull out all the corresponding labels. So class ID, which is the numeric class label, and we're going to append that to our label data set, and then we're going to put this into a nice, and then we're going to use this to form our training data for the model. Now this takes a little while, so I'll be back once this is done.
A little longer than a few minutes later.
Okay, we finished passing all of our audio files. We'll just double check that we have our array of features here. Let's just load this up. So you can see we've got multiple arrays in here, and these should be, let's check out the first one. These should be 128. So this corresponds to the shape of this mel frequent spectrogram, which is effectively the image we're going to feed into our convolutional neural network. So let's create our feature training data set. So we want to create an array. Let's call this temp. And we're going to feed in our feature and our labels. So let's just double check our labels are correct. So here we go. This is our label class 3. So we'll create our array of training data. Let's specify dtype equal to object. And then we want to transpose this so it fits the shape for the input for the neural network. Oops. So that's our training dataset created. So let's call our X and Y values. So the X, which are the features, are going to be the second axis, and the Y is going to be the first axis, the second axis rather. So let's just have a double check that these are the right shapes. So we've got two datasets there, one labels and one features, split, and they're both the same length, 8,732, which is the entire length of our Urban Sound 8K dataset. We called X here features X underscore because we actually want to do a second transform to make an empty array of the same size to train all of our data. So 8732 by 128. And we're going to say for I in range 8732. The x's of I are equal to x underscore I. So we just create this empty array to properly format the data for the for the model, and then we're going to say y to categorical y. So we'll just change those into categorical type data types for the model as well. So we can see that we've got our data shapes. So the training data is 8,732 long by 128, which is the shape of our image files, and then the Ys are 8,732 by 10, and 10 being the 10 different classes that we're actually classifying. So this is a kind of multi-class problem. So let's now split our data into our training and test set. So we'll call xtrain, xtest, ytrain. Ytest is equal to, and we're going to take the test train split function, train test split function, always get those the wrong way around, from sklearn that we referenced earlier, and we're going to call the x to y, and let's just call random state equal to 1, 2, 3. And actually, let's specify the test size. So let's call that 0.2. So we'll do a normal 80-20 split. You can see we've got the 80-20 split. We've got 6,985 training and about 1,700 test samples. So let's get into the modeling. Let's create our convolutional neural network. So this is going to be quite a simple model. We're just going to create a sequential model with a number of different dense layers. So let's create that now. So we created our model. We have a sequential model type with 1, 2, 3, 4, 5, 6 dense layers with ReLU activation. And then our output layer is a dense layer of 10, so our 10 different classes with an activation of softmax for multi-class classification outputs. So this gives the probability of each class as an output layer, which lets us see the class that we are most likely predicting. So let's start training our model. So we want to fit our optimizers first, so we'll call the Adam optimizer. We want to define what our loss is, so that is categorical cross entropy. And the metrics will be accuracy. And then we want to fit our model. So we're going to feed in our xtrain data, our ytrain, and then epochs, we'll say 90, batch size 50, and then validation data is equal to xtest, ytest. So we'll let this run. So let's just double check it training. It's training, it's good. We'll be back once this finishes training. So we're back, our model is trained, and we can see we've got a good validation accuracy of about 83%. We could do better, I'm sure, with a bit more feature engineering and time, but this is good enough for our purposes, which is for detecting gunshots. So let's have a look at our classes. Let's just remind ourselves of what they look like. So audio files. So we can see all of our different class IDs linked to their class names, gunshot being 6 that we're interested in, but we're obviously interested in making sure the model predicts all these other data types as well. So we actually need to predict in our model, we need to pass all of our audio files through to their spectrogram format. So let's put together a little parser to do that. So we've got a parser put together here. All that really does is just do some of the same things that we've already done throughout this whole notebook. So we're loading in the data, converting it to a mel spectrogram, and then we're just appending some of that to an array so that we can properly format that into the shape that the model expects. So let's just make sure that we've got that function loaded, and then what we can do is we can see if our model is working. So let's give let's pick a random audio file here. So I'll pop in our file name, we'll call our model, and we can see that the model's predicting children playing. The actual label is children playing. Let's have a listen. I think we're correct, that does look like children playing. So let's go back to our original index. Let's see if we can find our index here. So that was our gunshots. So we want to test that our gunshot's working. This was the file name. So we're in fold 1 and we're looking for 102.305.60. So this should be gunshot. Let's check if our crime detector can find the gunshots. And it has. It's predicted gunshot. The actual audio file is a gunshot. Let's have a listen. Perfect. Our model is now accurately predicting the sounds that we hear around the urban environment, and it's found gunshots. We can now detect crime across the city. Our model is working perfect.
There we have it. We've created our model that will accurately detect gunshot clips in the audio we hear around the city. Thanks for watching. The Kaggle notebook will be in the description below, and keep subscribed for more tutorials in the future.